Yes. Right. Good evening, fellow engineers and scientists. I'm so glad you've joined us. Thank you for coming. So before we get started, as I've just mentioned, some quick announcements. So we are recording this just for people that have joined. It will be made available to all of you in the public afterwards, so that'll be on the IMechE YouTube page. During the event, please make sure that your microphone and your camera are turned off. If you want to ask a question at the end, there's going to be a Q&A session. So at the end, raise your hand. Don't keep it raised throughout because we're not going to answer it. But there, in the Q&A session, you can be unmuted and you can speak your question. Or separately, you can use the chat box throughout the presentation, and then at the end, I'll read them out, and they'll be answered. So this is a 1-hour presentation, so we're going to have about 40 minutes from our guest speaker, followed by 15-20 minutes Q&A. So with all that out of the way, welcome, as I've said, to the second event in our Engineering Careers series. So as you may know, this series is showcasing disciplines, career pathways, and opportunities from all over the engineering industry. So we're planning to cater for engineers coming from and going to all walks of life, from students, professionals, civil, CFD specialists, the whole works. So our guest speaker today actually covers all those bases, and he is a frontier of specialist low energy solutions for developments ranging offices all the way to laboratories. He balances functional, aspirational, and sustainable performance, all while satisfying excellent quality targets, building regulations, and local planning permission. So it is my privilege to introduce University of Cambridge alumnus, Associate Director of AECOM, and IMechE Chartered Engineer, Mr. Matthew Butler. Over to you, Matthew.
Thank you very much. So apart from me, this presentation's about the Centre for Sustainable Chemistry, otherwise known as the Carbon Neutral Laboratory, that we built for the University of Nottingham about 4 years ago now. So about me, I got interested in engineering quite young. This is a photo of me at the Davy Distington factory looking at one of the channel tunnel machines that they had pre-assembled before sending it down to Kent to dig one of the support tunnels for the channel tunnel. Quite a big machine. So in a way, my career has been quite simple. I did a year in industry before university at a company called Caverna Metals, who made machinery for steel rolling mills. I went to University of Cambridge, where I studied mechanical engineering for an MIMechE. And while I was there, I went to careers fair, and at the time had a quick chat with somebody from a firm called Oscar Faber. They invited me to an interview, which obviously went well. They offered me a job, and then by the time I joined, Oscar Faber had been bought by an American company called AECOM, who combined them with another company they owned called Maunsell to create something they called Faber Maunsell. So that was the name of the company that I joined, and eventually in 2009 they rebranded Faber Maunsell as AECOM, which is the name it is now. It took me a while to get chartered, I have to admit. Never quite got around to doing the forms, but eventually in 2018 I became a chartered engineer with IMechE. In terms of what I've actually done with AECOM over the years, I've worked on a very wide breadth of buildings, which is one of the reasons why I wanted to be a consultant engineer. So I had a breadth of projects to work on. This is one of the first projects I worked on, which is referred to as the Southfields project at Hinxton, which is a Wellcome Trust site. And it's where they sequenced the first human genome, just beating the Americans to it. At the time they were sequencing it, they had some big lorry trailers in this car park area with computer equipment in to do that first sequence. The project I worked on was all of these buildings, which would basically support the ongoing research into the human genome. So there's a big data center and wet laboratories where they can do experiments, and a support facility, and very importantly, this is the catering facilities. And I worked across these buildings, so looking at the chilled water system in the data center, optimizing it for resiliency, and I had a lot of involvement in the laboratories, which is one of the main areas in my career since, and looking at early energy efficiency examples, like putting heat recovery on the ventilation to it, which can be quite a challenging thing to do with laboratories. Oh, and I've actually done my summary for myself here, which I forgot about, but anyway. And you can see this is a picture of the laboratories in there, and this is a data center, which is quite unusual. Most data centers don't show themselves off to the world, but the Wellcome Trust, they wanted to show what they were doing. So there's big glass windows that you can see into the computers inside the data halls. And this here is the wet laboratories. A bit later on, I worked on what at the time was the largest hotel in the UK. I suspect it still is. It's over 600 bedrooms. I found out when I was putting these slides together, it was awarded the best airport hotel in 2009 as well, a year after completion. It was an unusual project to work on, as normally when I'm sizing HVAC equipment, we have to make sure it's not too noisy outside to make sure we don't disturb the neighbours and make sure the fans don't transmit too much noise inside. But we had the additional factor that we had to make sure we attenuated the noise of the aircraft taking off, so we didn't wake people up with the early morning flights. And I also developed an energy efficient bedroom temperature control system that used the booking system to optimize when the cooling and heating in the bedrooms was turned on, so that the hotel wasn't wasting energy air conditioning empty rooms. And then moving on to a slightly different area, I worked on the development of an academy for the Isle of Sheppey, which was a bit of a challenge because it was across 2 sites, one of which was on a hillside, so a bit of a challenge in terms of the grade, and then the other one was right next to the sea and in a flood zone, so 2 very different aspects. And as far as my involvement, a lot of that was modeling the natural ventilation to make sure we could keep all the students comfortable and not too hot. Then in 2015, I worked on an extension to the engineering department in Cambridge, which was quite nice, going back and seeing the building again and seeing how it was getting on. It was good as an energy efficiency project because they set a reasonable target of a low energy consumption of 100 kilowatt hours per meter square per annum, and you'll see later how that compares to other buildings, because they said they didn't want something that was too much money in terms of installing a whole load of PV arrays and things like that, but they wanted something that was just low energy, which is what we delivered to them, including a very successful natural ventilation design. I got feedback from the engineering department this year actually that when it hits, I think 34 degrees C outside, it stayed at about 30 degrees C inside, which is quite impressive given there's no active cooling at all. And then in 2018, you may have heard of the London School of Hygiene and Tropical Medicine recently, as they've been in the news quite a lot, as they are quite involved into research into COVID-19. I'm not probably not the laboratories we looked at, because these were malaria labs, but this was an interesting thing that is happening more often in terms of we were installing this block here was built as offices about 10 years ago, and they were looking to refurbish them as laboratory space instead to meet their growing laboratory requirements. So we had to slot into an existing building on a very tight site, some highly serviced laboratories, which included installing some big air handling unit equipment on the roof, which has also given them the flexibility that this has the capacity to enable them to install laboratories on the other floors of this building and in floors on adjacent buildings. So that's a quick summary of me so far. And this is one of my, I guess, favorite buildings. And I think, yeah, good buildings that I've worked on, which is the Centre for Sustainable Chemistry. To give you a bit of a context, laboratories are very high energy consuming buildings. This is some data that an architect from HOK helpfully put together, which is a summary of some benchmarking energy consumption figures for various different typical laboratories. And you can see that there's sort of they average somewhere between 600 and 700 kilowatt hours per meter squared energy consumption, which when you compare it to the target for the Dyson building that we were given of 100 kilowatt hours per meter squared is a lot. And even if you look at a typical office building at only 200, you're looking at 3 or 4 times the energy used for an office building. So it's very important that we reduce that energy consumption if we're going to get anywhere near to our carbon neutral aspirations as a country. But in terms of the Centre for Sustainable Chemistry, it's summed up very well by Peter Lysons, who is the professor who runs the building as the centre director, in terms of, he says, this is bigger than just a building, it's a whole philosophy. Because as well as being a very low energy carbon neutral building, the Centre for Sustainable Chemistry also hosts the University of Nottingham's Centre for Sustainable Chemistry, where they research technologies for future sustainable chemistry. So it's not just low carbon. They research things like photovoltaic panels, but quite often they're researching how to use fewer of the more less available elements and things like that, and the elements that are more destructive to the environment. So it's sustainability from the full range of aspects. The original concept for the building actually came from GSK. They, way back in, well, I believe it was about 2010, 2008, they set an aspiration that they wanted to be carbon neutral by 2050, which I believe was quite groundbreaking at the time, before a lot of other companies. So they went to an architect who specialised in low energy buildings, called Bill Dunster, and they asked him to look at a concept of how a low energy lab might work, which apparently his response was, I don't know anything about laboratory design. And they said, that's the point. They wanted a fresh look at it. Then after he'd worked out his concept, they came to us at AECOM to see whether we could validate, using our experience of laboratory design, whether his low energy concepts could work. So they included things like natural ventilation, using the pressure across the central ridge on the building, and obviously a large PV array. And also they were looking at things like, they wanted it to be a low energy building for low energy chemistry, because they have lots of big energy hungry buildings that are designed to be ultra safe to use and people can do all kinds of experiments in, but not all experiments are actually using dangerous chemicals. So they realized that they could have a lower energy building suitable for people to do, I guess you could call it lighter chemistry, chemistry that didn't need these big energy hungry facilities, so they could help to get their carbon footprint down. So that was GSK's concept. At the time, they decided they didn't have the place where they would actually develop this building, so instead they gifted the money to build it to the University of Nottingham. To give us a challenge, the University of Nottingham said, okay, this building with low energy science is very nice, but we need a building for our Centre for Sustainable Chemistry, and that is a full chemistry department, and we can't just have low energy chemistry in it. So they insisted on us building them a fully functional, full-on chemistry laboratory with lots of energy hungry equipment like NMRs, nuclear magnetic resonance, which are liquid helium cooled equipment with big magnets in that use a lot of energy and use it 24/7, which is quite challenging. And also we have lots of fume cupboards, which are important because they keep scientists safe. They allow them to do experiments, and they also allow us to reduce energy by preventing us having to ventilate whole laboratories to very high ventilation rates to keep people safe. We can enclose experiments in them, but they do use a lot of energy themselves. I worked out that a typical fume cupboard probably uses about as much energy as a 1-bedroom flat, which is quite a lot. And then it has all the other things you'd find in a laboratory, like write-up spaces where people can write up the results of their experiments, and offices for the professors and other lucky staff, I guess. One unusual feature for a laboratory building is it has a winter garden, which is there to provide a thermal buffer to the ambient temperature by having south-facing glazing that captures heat from the sun in winter to help warm the building, and with a large overhang of PV that shades the building in summer. It also provides a very nice eating and drinking and social area. So in terms of the concept, there's three main aspects in terms of aiming for this zero carbon label. Firstly, we have low energy consumption. It's absolutely critical that we reduce all the energy consumption in the building as possible, because we want to be pulling in as little power from the grid as we possibly can. I'll explain a bit later, but we couldn't use the natural ventilation in the original concept because of the requirement for more intense chemistry. So we use the wind to help drive the ventilation, but it's still mechanical in most areas. We have low energy fume cupboards. Very importantly, we localize ventilation systems. Rather than have big AHUs centrally, we put them local to the area they're serving, so they provide exactly the right airflow at exactly the right temperatures, rather than having big central systems that are very inefficient. The off state is important. We need to switch the building off at night, and fabric as well, insulation. And then to get zero carbon, you also need to make sure your structure is very low in embodied carbon, which is something that's become more in the press recently. So we use timber because that actually takes carbon in from the atmosphere, so effectively sequesters it. And then we try and use natural materials throughout, which are naturally low in carbon. And also we try and minimize how far we're transporting the material. And then the last bit, and it's very much is the last bit, any carbon we can't design out or energy consumption we can't design out, we offset with renewable energy. So there's a very large area of PV on the roof, which is a pitched roof to give us as bigger area of south-facing roof as we can. And then finally, we have a biofuel CHP, which provides us with both low carbon heat and low carbon power, which was part of the design that we had to add in to suit the higher energy chemistry that the University of Nottingham wanted to do in the building. In terms of the off state, this is absolutely important, because if you think about how people work, you typically have an 8-hour working day. And if you think about the building, your office even, that you might work in, for the other 16 hours, it's unoccupied. So potentially you can use more energy in a building when there's nobody in it, not using it, than you do when they're there. So it's very important that we design buildings to be off when they're not required, to be off when they're unoccupied. So in terms of one of the basic low energy concepts was reducing fume cupboard usage. So reducing the energy from the fume cupboards. So there's two main ways we targeted doing that. One of them was we provide something called a ventilated enclosure. So a fume cupboard allows you to work on an experiment while it's in operation. So it provides you with protection. These ventilated enclosures allowed the scientists to set up an experiment and then shut it away. And then it was only safe when it was shut away. So it suits a different kind of science, but allows them to do science in a lower energy way when it's possible. So that saves us energy by reducing the energy consumption of these high energy fume cupboards. The other important thing is chemical storage, which is quite a basic idea, that instead of scientists have a habit of storing their chemicals in a fume cupboard. So you have this thing that uses as much energy as a one-bedroom flat, and you're using it to store vials of chemicals, which makes no sense. So instead of doing that, we get them to turn the fume cupboards off at night and just put them in a cupboard, which has an extract rate of 2 liters per second, which uses a fraction of the energy of the fume cupboard. That will keep the chemicals safe overnight when they're not there, for a lot lower energy. Then we still needed the fume cupboards because they're an absolutely critical part for the science and for keeping the scientists safe, but we then designed them to be as low energy as possible. Like I was saying before, we provided a separate ventilation system for each lab to make sure it was as low energy as possible, with the supply and extract requirements exactly match to each lab. There's something called a low face velocity to the fume covers, so they're designed to require as little possible airflow through them to keep the scientists safe. They're all variable air volume, so that the airflow through them varies depending on how high the sash is on the unit. Importantly, the units can be turned off. Quite often, fume cupboards are designed so they're kept on 24/7, and that keeps using energy. But ours are designed so when they're not used, the user can turn them off. And also, there's one big element was educating the scientists. They can traditionally scientists can have a habit of thinking that they own a particular fume cupboard, that it's there to use, whereas the scientists have moved to a more sustainable way of working in terms of they share the fume covers and they share the facilities more. So as I was saying, the embodied carbon of the building is an important part of this sort of zero carbon equation as well. So looking at the materials is very important. There's a lot of use of timber. The structure throughout is timber. The partitions are made of timber, whereas normally they would be plasterboard. The floors are timber. Everything is timber, which makes it look amazing. And then there's little details like there's terracotta cladding on the outside of the building, which is reasonably high energy because you have to fire it in a kiln. But terracotta is normally twice fired. This terracotta cladding is just once fired, which still works, but it's half the energy. It's really simple. On the roof, we have not just a green roof, but a diverse species roof. It has lots of different wildflowers on it and looks gorgeous and pretty when it's in flower at the right time. And also, as well as low carbon, just environmentally sustainable was very important to us. We were making sure that we had materials that would not affect the environment apart from just the carbon content. So things like the fume extract ductwork you can see here. This is it needs to be plastic so it doesn't get rotted by the chemicals in the fumes, but it's PPE, polypropylene, instead of PVC, polyvinyl chloride, which would be conventional, because the chloride in the polyvinyl chloride, that's very harmful to the environment and inevitably leaks out during the manufacturing process. So the PPE is a lot better for the environment. Another aspect in terms of the low carbon was the supply ductwork, which is this, you can see is this white circular element here. It's made from slabs of insulation. There's no actual metal ductwork inside of it. So we just use the insulation, which would require anyway to carry the air, which again saves on the embodied carbon. And there's obvious things like we've got LED lighting throughout, which is just a given in a modern building. It's so much lower energy than any of the alternatives. And we also have some other neat things like the urinals. We wanted to have as low water usage as possible, but we didn't really want to have waterless urinals because they require nasty chemicals to stop them smelling too much. So we have a system installed called an air flush, where a little fan constantly pulls air from the draining system, pulling air in through the drainage holes in the urinals, which stops the smell at a very low energy usage and with no chemicals and with no water usage. So in terms of our carbon solution, we end up with having our embodied carbon in the construction, emissions associated with the energy use in the building, which is offset by the power we generate from the PV array, and the heat and power we generate from our biofuel CHP. Which one important aspect I didn't mention as well was that biofuel CHPs are challenging because some biofuels offset, well, if we use food-based crops for biofuels, we risk affecting supply of food for people. So our CHP uses what's referred to as a second generation biofuel. So it's an industrial byproduct. So it doesn't affect food consumption at all. So in terms of that carbon solution in a bit more detail, you can see that for this concept, we use the grid as a battery. Probably if we were designing now, we'd actually have battery storage because it's come on a long way since we did the design for this. But At the time, we're effectively considering the grid to be a storage of energy for us. So in winter, when there's more heating demand, we generate more power from the CHP, and so our net imported carbon, that's this red line, is negative. So we are exporting more energy than we're using. So we are offsetting what little embodied carbon there is in the construction. And then in the summer, we do get more PV power generation, but not quite enough to offset the lower heating demands. So we have to draw in a little bit more power from the grid than we are exporting. But overall, over the year, we end up with a net negative carbon, or at least that's the target. And in terms of that embodied carbon in the building, I always find this graph is interesting because this shows the embodied carbon of the different elements in the building. Now, normally in a building, this element, that is the frame, would be huge because this would be concrete or steel or something that takes a lot of energy like that, and would probably be somewhere off the scale, 5 times or something as big as anything else. But because our frame is timber, that value is actually slightly negative because of the embodied carbon content of it. So this is quite different to your standard building, and everything has been targeted to be low carbon. So even the foundations, which we couldn't make from timber because they would rot, but normally they would be concrete, but they are actually just columns of stone that are vibrated to give them their structural strength. The building services then unfortunately comes out as looking like one of the biggest carbon containing elements, which it is for this building, because again, we couldn't make it all out of timber. Unfortunately, electricity doesn't travel very well through timber, so they had to be copper wires and things like that. But we reduced their embodied carbon as much as we could. Little things like prefabricating elements to install safe carbon, because we don't get as much wastage. It's a lot neater and tidier to make something in a factory than it is to make it inside a building, which is effectively a temporary factory, just not as well set up as a factory. So overall, this gives us this carbon payback graph, where the orange is the embodied carbon, this is the embodied carbon construction, and it goes up over time as we are anticipating that the building will be refurbished and there will be life cycle replacement of equipment, particularly the MEP equipment. And then the blue is the offset carbon, the offset electricity, excess energy we're generating from the building that offsets that embodied carbon. So overall, the red line shows our journey to be net zero carbon. So actually, in the original model, we achieved that net zero carbon after 10 years. And just to get an idea of how low carbon we've got the building to be, this is some typical benchmarking data from other buildings, and you can see that a typical laboratory building is over 4 times the embodied carbon of the sustainable chemistry building. Now, one thing that comes up a lot from people is people assuming that this has to cost a lot. And I assumed it was a premium building as well, in all honesty, because it looks gorgeous. It's, in terms of a laboratory building, it's definitely one of the best I've ever seen. But actually, my quantity surveying colleagues did some benchmarking against some other buildings that they had data for, and it actually comes out very low, which is remarkable for something that delivers a beautiful building to work in, is sustainable for the future, and doesn't cost a premium, which shows that, being good for the environment, it can save us money. And actually, they also developed a concept where they thought they could get the cost down for a low carbon laboratory even lower. So one of the things that I think is really important about this building is that, as well as being a laboratory for the chemistry, it's also a laboratory for low energy design. So we have lots of metering in throughout the building, and we are reviewing and keeping an eye on what is happening in the building, and both feeding back to the users to help them with how they can improve how they're working to be lower energy and more sustainable, but also to help us guide our design and other consultants' designs to be more energy efficient in the future. So this example is the power consumption in the laboratories. And you can see the orange line is the target we set them. So importantly, you can see that the power consumption drops right back overnight. We expected them to turn off any equipment they didn't need overnight because they weren't there. There's always a small amount of usage because there's always some equipment in the laboratories that they can't turn off, but it should be very low level. And you can see that the reaction to this has been varied. Laboratory 4, fantastic. They've been very low energy. They're very low energy and they're very much meeting what we targeted them with. Laboratory 1, less so. They are not turning stuff at night and using a bit too much energy during the day. In terms of the energy consumption during the day when they're there, I'm in two minds about this because it might just mean they're doing more science, which is fantastic because ultimately the best thing is that the building gets heavily used. So I wouldn't want to punish them too much for that, but definitely not turning things off at night. That's something where they could definitely improve. We've also played around a little bit with better ways of representing the data. And this is a heat map for laboratory 3, which you can see was this graph here. So one of the ones that wasn't doing that well at turning off at night and was reasonable during the day. And you can see that actually you can track how they're using it and track how the scientists work. That you see the red blobs, they're the weekdays. And you can see at weekends, they're quite good at turning stuff off, and they're very good at not working weekends, which is great. But there appears to be a fairly consistent midweek. Maybe it's a rush and they leave equipment on overnight. Maybe they want to get more done on a Wednesday. But it's these kind of areas of leaving equipment on overnight that they really want to target. Yeah, so here you can see weekend turning off, great. Midweek, not turning it off, not so great. Now, in terms of the ventilation, as I said, we put in local air handling units to really try and get the energy consumption down. Unfortunately, so far it's not been working as well as we hoped. You can see here that the orange track again is what we were hoping for from our model. The purple is the actual recorded data, and you can see actually it's not turning off at night like it should do. What we've identified is this is down to the controls because we are needing to be very careful with the controls because we need to make sure that any scientists who decided to work in the middle of the night could do so safely. And what we're finding is those controls are so safe that they're not actually turning the ventilation down to the low rates that they should be at night. So we have recently been exploring this with the University of Nottingham and their controls engineers, and we're currently looking at solutions on how we can actually get this all-important off state to happen. With comparison to GSK, one of the things they do is because they recognize that this out of hours usage is so high, they actually tell their scientists they can only work office hours. They kick them out at 6 o'clock and don't allow them back until 8 o'clock in the morning. They don't allow out of hours working, which is a very effective way of saving energy. So that means they can, with confidence, turn the majority of their systems off at night. One good thing about the ventilation is you can see that actually the fume cupboard usage has been very good during the day, and it looks like the scientists are being good and efficient with using them. So we're not getting as much energy consumption from the fume cupboards during the day. So that's a very positive thing. You can also see how the ventilation consumption varies with the heating demand because we're getting a high heating demand at night, which again reflects that excess ventilation overnight. So one aspect that is very important about the design is this localized ventilation. And within the building, we have 4 laboratories. So we don't have any cooling generically, apart from we have 4 laboratories which were designed specifically to enable them to have equipment that was more temperature sensitive that required cooling. 2 of them are just general laboratories, and 2 of them have the NMR equipment that I mentioned earlier, which for reference represents about 25% of the energy consumption of the building. So for those equipment laboratories, the localized ventilation is absolutely critical for gaining a low energy performance. If we were doing a conventional laboratory building, or actually quite frequently office buildings, we would have a big centralized air handling unit that would provide the ventilation requirements for the laboratories and would supply air at around about room temperature. And then within each equipment laboratory, we would have fan coil units, which would provide whatever heating and cooling is required to keep the space at its required temperature. The big problem with this is that we're taking outside air at maybe 12 degrees C. We warm it up. We use heat recovery, so it doesn't use too much heating, but we warm it up and supply it into the room. Then the room, because it's got lots of equipment in, needs cooling, so we then provide lots of cooling through the fan coil unit to cool the room down. Where instead, if we can have an air handling unit dedicated to each room, we can take that 12 degrees C air in and we can do nothing to it. We can just blow it out straight into the equipment laboratory and meet the cooling demands it needs. So we can save a lot of energy by having these local air handling units that provide just the right temperatures to meet the heating and cooling requirements of the laboratory and just the right airflows. So in terms of how that looks in figures, this is a chart of how we estimated the energy consumption for the cooling demand for these equipment rooms. I'll explain why later, but I've normalized the cooling consumption against the power consumption in the equipment laboratories, which is a good estimation for what the actual sort of heat rejection requirement of the laboratory would be. And you can see that basically you can see all this free cooling we're getting from the fresh air down here. Because the density of some of these rooms is quite high in terms of equipment, it starts to rise up when the temperature is fairly low, but we're still getting free cooling. So wherever the temperature is below 1, we're basically getting free cooling out of the fresh air. And then when it goes above 1, we are then having to put more cooling in than the actual space demand to sort of cool the outside air temperature down as well. Now, these yellow dots are what we've measured from the actual recorded data on site, and it's actually remarkably well matching the model. We're still about, our cooling demand is still about 30% higher than the model, and again, I think this is down to controls, which is increasingly appearing to be one of the biggest energy consumers. And it's not necessarily bad controls, but it's just that controls can never be perfect. They can never exactly match the demand. So however much we try, we're always going to overshoot, undershoot in terms of heating and cooling, and that just adds that little bit of extra energy consumption. But to compare, the orange triangles are our estimation of how much cooling energy we would be using if we had a central system. So we were having to heat and cool the air at that central air handling unit and then provide the cooling in the space. And you can see that obviously there's no free cooling. So we're getting a lot more cooling consumption. And overall, on an annualized basis, it's about that would have been 3 times the cooling demand that we have for our rooms with the local ventilation system. So that's a big saving. Another interesting one is water consumption. This is from a model which we used the guidance from the Institute of Public Health Engineers in terms of what laboratory use we would expect in a laboratory, water use we would expect in a laboratory. And then the yellow figures are what we recorded in 2017, which is a lot lower. You can see it's only 20% of that design value. And this is important because it shows that the scientists are a lot more efficient with the water consumption than is assumed, but also it means that in future we can size equipment to be smaller. We can put in smaller water storage tanks because we don't need to store as much water. We can put in smaller pipes, and we can save on copper, which is a big both source of embodied carbon, but is also a finite resource. So by using this data and using the feedback, we can optimize our designs. As we go through the years, and you can see we've got 2018, 2019, 2020 data here. We don't have 2021 data, partly because obviously it's slightly unusual compared to normal. But you can see there's a general trend of only 30% of design in terms of water consumption. There are some outliers, and I mentioned the green roof. The green roof was meant to require no watering. However, 2018 was a particularly hot, dry summer. And so, unfortunately, the university had to use the hose quite a lot to keep it alive, which is frustrating. If we'd have known that actually it would require watering, we would have put in water harvesting to store water to water it. But that would be, again, a lessons learned. Hot water consumption is, again, an area that is quite different to the standard design and an important energy consumer. In terms of the heat to generate it, the orange was our idealized design. The peak at the start is basically the hot water storage being heated up at the start of the day, and then the consumption through the day, and then dropping off towards the end of the day. In reality, the university have demanded that the hot water system is kept on 24/7. And while we can see in the water consumption figures that there's no usage at night, you can see here, this is a demand graph, there's still energy consumption. And this is just keeping the hot water pipes hot. So we end up with as much heating demand for the hot water to keep the pipes hot as we do to actually supply the water for people to draw out of the taps. Which is really important because it shows that actually maybe things like local hot water generation using things like electric resistive heating, which is normally not that efficient, actually on aggregate is far more efficient because we don't have the losses associated with pumping all this hot water around the building. The actual hot water consumption, you can see here, this graph does actually show the recorded data we got through the years 2017, 2018, 2019, 2020, which is a fraction of the public health engineers' guidance. And I've shifted the graph onto a log scale so you can actually see it. And our hot water consumption is only 1.5% of design, which again leads us back to the thought of actually local electric hot water heating. Something like that would make more sense because it should be lower embodied carbon because we haven't got as much distribution pipe work and big central hot water generation. And because the hot water consumption is actually quite a small proportion of what we thought it was, the energy impact would be fairly low. So in terms of the annual energy consumption, on the left, you can see the annual power consumption. Top bar is our actual consumption. To give an idea, the HEPE is a body who benchmark higher education facilities, and this is a benchmark for how much they expect a laboratory building to use. And so we are a lot lower than the benchmark. BRUCL is the standard building regulations compliance model, which people sometimes use for energy predictions for building. And you can see it's a long way out from the actual building. And this is a big problem because people can design based on the performance they get from this and think they're getting an energy efficient building, when actually it has lots of assumptions in it, which allow it to produce a simple model, but can miss subtleties in low energy design. At the bottom, we've got what our model predicted with the energy consumption, and we're reasonably close. Not perfect, but it's not too bad, I don't think. You can see that the scientists are using about the same amount of power as predicted, possibly too much at night, a bit less during the day, so hopefully we can sort that out. The fans and pumps are using about twice what we targeted, which is not ideal. But again, that appears to be because our handling units aren't turning down properly overnight, which is something we're working on with the university. In terms of heat consumption, this is definitely too high. Still a lot lower than the benchmark. Again, the BRUCL just shows silly values. And it is a lot higher than our model. And again, we think this is mainly due to the ventilation system not turning off at night properly. And so in terms of the REBA 2030 climate challenge, and this is again using the data I referred to earlier, we're actually, even though we're not getting anywhere near model, we're doing very well compared to what REBA have identified a laboratory building should achieve in terms of a performance. So REBA have identified that they reckon that by 2030 we should be achieving about 200 kilowatt hours per meter squared of energy consumption for a laboratory building, and we are at about 300 kilowatt hours per meter squared without renewables, 220 with. So actually we are not that far off, and we've estimated that if we can sort out the controls issues we have, we can hit that 2030 target about 9 years before it's due. In terms of the carbon emissions, unfortunately, we're not quite getting to where we need to be. The model here, you can see this is a negative around about 100 tons of CO2 per annum. Just in terms of on the right hand side, you've got the carbon inputs, so the consumption of power in the building, and then on the left hand side you've got the carbon offsets, and the biofuel, because it has a very small carbon content, and on the left hand side you've got the offsets, so the power generated by the PV and the power generated by the CHP and heat that we export. We haven't managed carbon neutrality last year, unfortunately. One of the main reasons was the CHP engine proved to be very challenging. They're very temperamental, very difficult to set up, very difficult to commission to do what they need to be, and our one blew up, which was unfortunate. It has now been repaired and is up and running again, so we're hoping to get better results this year, or last year, which we haven't analysed yet. But we estimate that if we had the full CHPA available, we would have been just shy of negative carbon. Not quite the target, but pretty good. One of the aspects in the original concept was we would be exporting excess heat from the CHP that the building didn't need to some adjacent buildings. Unfortunately, that system wasn't up and available last year. But if that had been available, we estimated we would have been well underneath the carbon emission target. So, in summary, I guess this is a picture of one of the laboratories, which is a gorgeous space to work in. Frankly, they get lots of natural light and they are beautiful airy spaces, and we get lots of good feedback about how inspiring and nice the building is to work in. So not only is it sustainable, it's also an inspiring building. And that's me, and I guess over to questions.
Wow, that was really interesting. Don't you think, Michael?
Yeah. Really
I didn't expect. That was really enlightening. I have to say, I didn't expect half those things to come up, but it's really, I was really impressed.
Yeah,
It's a bit concerning, but never mind. So
I have to admit, I was a bit worried because it's quiet. You're kind of like, I haven't put myself on mute or something, have I? I am still,
I should have been nodding along, left the camera on. Yeah. So now we're going to turn to our listeners for the Q&A. So, audience, whatever field you're in, if you're a student, he's been to Cambridge, he's done a placement, he's done all those. Obviously, he's worked with medical, he's with GSK, he's done civil, because he's literally built a lab. So remember to put your hands up using the raise hand button, and that's in the top right. Yeah, let's hear your questions. Give them a type, raise your hand.
Definitely, I'd say there is actually quite a lot that goes into the design of the buildings. I had a question for you, Matt. How long roughly would you say the design process is, and roughly like how many iterations of the design go forward before you get like a final design?
That's a fascinating question. Yeah, it depends a lot on the building. So this particular building, well, if I just take the building we built for the University of Nottingham, because the concept for GSK is like an added extra, that was about 2 years in total in terms of design. There's a standard design process that's set out by RIBA, who are the Royal Institute of British Architects, that has 5 stages of design. Well, it's 6 because there's a 0. But that gives you a pretty good idea of the iteration. So you start off at 0, where you're just literally kind of going, what might we want?
Yeah.
What does the client, somebody's got an idea of I might want a new building, and that's kind of working out what do we actually want a new building, or could we just use that empty classroom we've got over there, or do we actually need a new building, and that kind of stuff. And then working through stage, I can't remember all the names of the stages, but exactly what they are. But stage 1, that's very much the sort of the feasibility design. So once you've worked out you actually want a building, can you deliver it? You know, have you got a plot of land that's big enough for it? Or, you know, have you got the money for it? And those kind of things. And then stage 2, where you develop a concept about how it might look and what might go into it. And then stage 3, where you're sort of developing the design more, really fleshing out that concept. And stage 4, where as a consultant, that's normally where we design to. And so we design for construction in terms of having everything in the building. Then stage 5 is construction, where the contractor will take on board our design and develop drawings so he can actually install things. So subtleties like we have ductwork, we'll normally just draw a length of ductwork, and he'll take that ductwork and kind of go, okay, I'm going to build that in meter-long sections, say, so I'm going to have flanges between it. So he'll add the elements that actually make it buildable, and so how he can put it together, if that makes sense.
Yeah, it does.
You know, saying it takes 2 years. As I also work in data centers, which I struggle to put any slides up because they tend to be very private, so you can't talk about them. But sometimes we can deliver very big data centers in terms of designs in 6 months or less, because they're pushing and they want it now. So it depends a lot on the type of client and how much they're pushing for it. And also designs can extend because clients change their minds. And you get halfway through the design process and they suddenly go, oh, yeah, we've got a new department we want to put in this building. Or, you know, or quite often, oh, we've just got another source of funding, we can add an extra wing. Or we've just lost half our funding, we need to chop half the building up. You know, those kind of things.
Yeah. Great. We have a couple questions in the chat box. We have a question from Chris. It says, did you consider wind power as an additional source of energy? And wasn't the water harvesting a bit of a dropped ball?
Yeah, good point. Okay, so wind power. Wind power on buildings doesn't work, basically. There's too much turbulence around them, and there's various effects where the wind speed drops rapidly as you get near the ground. So as part of the reason why wind turbines are on tall towers, apart from because they've got long blades, is to get them away from the ground effect where the wind speed drops a lot. So people have tried over many years installing wind turbines of various sorts of buildings, and I think there's a big building in South London with 2 wind turbines in it that I don't think you ever see turning, which shows you how difficult it is. So it basically just doesn't work, and it's been shown over many years that it doesn't work. So we very briefly considered it, but we knew from experience that it wasn't really a concept that works. A wind turbine standalone would be great, but there's not the space here. We couldn't get it far enough away from the building to get that to work. In terms of the water harvesting, I guess, yes, it's a drop ball, but this building it's an experiment. It's a laboratory to learn. The analysis we did showed we didn't need it because we have low water usage fittings throughout the building. So we've done within the building, it's designed to consume very little water rather than harvesting water. And because we had the air flush urinals, we didn't have that normal water consumption of flushing urinals, which would normally be a big driver for having water harvesting. And we were assured by the suppliers of the green roof it didn't need watering. So sometimes you have to take on board what the experts tell you, and the experts can be wrong. But you know, you have to learn. Every single design is never going to be perfect, and it's, I guess, where, say, people in the aircraft industry have an advantage over us. They get to build prototypes. They get to build a couple, maybe crash 1 or 2. I don't know, probably not. You don't really want to crash them, they're expensive. But you know, whereas in the building industry, one of the disadvantages and one of the great things about it is you only build one. You build one example, and that's it. And it's got to be right first time. And so getting it absolutely spot on right first time is unlikely, but you get it as close as you can.
Great. We have a question from Emily Howells. It says, how far off do you think we are from making all new buildings carbon, or zero carbon? And how viable do you think this is?
So having done a zero carbon building, I would say it's not actually necessary. Sorry, there's various different definitions. So this zero carbon building is about it being zero carbon on the site. And the government are sort of targeting zero carbon buildings, but they're fudging it slightly and allowing you to generate the power off site, not necessarily on the building. And to me, that makes sense, because if you can get, I don't know, 200 kilowatt hours per meter, 200 kilowatt hours of power generated off site for the same money that you could get 100 kilowatt hours per meter, 100 kilowatt hours generated on site, you might as well spend the money where it's more effective. So, and we have a national grid, we have a way of transporting energy around the country, so you don't necessarily have to do everything within your building. What we do need to do is get them to be lower energy. We do need to reduce that energy consumption as much as possible, so we can install enough renewables in the grid so that we can generate all the power we need to be low carbon. So, and I'm just trying to remember, was it about new buildings or all buildings?
All new buildings.
All new buildings could be effectively zero carbon, like tomorrow, probably, you know, quite quickly. We could, maybe not all new buildings. So office buildings are definitely somewhere where they could be. Hang on a minute, let's stop. No, probably not. we could be doing a lot better than we can do, but we hold back a lot. You know, people don't want to spend the money on it. They don't want to put the investment up. We like to do what we like to do. We like to have air-conditioned offices. We don't want to necessarily accept just a naturally ventilated office. So it's more I'd say there's still technical challenges, but it's more a human interaction challenge in terms of what people want and persuading people that they can living in an environment that's lower energy. But having said that, I'm trying to remember the name of one of the big major banks recently built their big statement building that cost a fortune and is fully green and fully low carbon and things like that. So even the big players who would expect to have a big air-conditioned office, when they have a mind to, and they'll throw money at things, they can do it. So we can do it now. It costs money. And also there's a perception of people, and people don't like things. So things like we need to use heat pumps for heating because they're low carbon. But a lot of facilities engineers, they don't like them that much. And they are a bit finicky and they break down more than boilers. So they're a bit more awkward to use. So we've got to accept the fact that our lives are going to be more difficult to be lower carbon.
Great. That definitely answers the question. We have quite a few questions.
Yeah, we had a few come in. We've got one come in from Alex Edwards, who asks, what can we do in the building industry to ensure that the buildings are constructed according to design and have energy ratings that say they do?
Yeah. Okay. So my personal opinion, and I keep banging on to people about this, is we need to start treating Bruckle certificates as just a tick in the box, something we have to do. We have to stop treating it as being a measure of how efficient a building is, because it's not. We need to actually start looking at our buildings and genuinely looking at how the systems work and how much energy is going to consumed. The Americans have something called ASHRAE, what's it called? ASHRAE 90.1, which is actually a full energy modeling standard. And it goes into a lot of detail. Whenever we think we might have to do it for a project, we try and avoid it because it's going to cost us a lot of money to do, which we shouldn't do. And I don't think we would do now, actually, because as a company, we are actually pushing to do real world energy modeling on every building. But so we should be, what we need to do is we need to actually have a new standard for doing energy modeling that actually genuinely models the energy in the building. And even if we're not using the building regulations model, the building regulations model is based on something called the NCM methodology. And people, even when they don't use the building regulations model, have a habit of using the NCM methodology, which again makes these basic false assumptions. One of them is, to give you an example of the standard methodology. And to be fair, there are assumptions that are made to make the modeling easier. But it assumes that fresh air is supplied directly into a room. It does. So even if you have a central air handling unit, heating and cooling it to room temperature, like I described, it assumes that it's supplied directly to the room, and then any heat recovery or whatever happens at the room level. So basically, I was showing the fact that we get big energy saving from free cooling from the fresh air. It assumes that that happens in your building, whether or not you've designed your systems to do it. So, which means that then people are not encouraged to design buildings to take advantage of that, because the building regulations assume it's happening anyway. So then we design buildings that are at higher energy because we're not pushed to do the energy efficient things, because what we're using for the energy model isn't right. So we need a new methodology, and we need people to genuinely, we need modelers, and we need more engineers to be involved in the modeling, because quite frankly, designing a building and farming it off to somebody over in the other side of the office and saying, model this building for me, and they do some modeling, they don't really understand how it works because they're just the modeler. And then the engineer doesn't really understand how the energy works because he's just the engineer. So the engineers and the energy modelers, they need to be combining together and really understanding how both of them work together and how the systems are going to work and react, I guess.
So we need a bit more clarity. So lawyers among us, I think we're nearing the end of our time, but I reckon we've got time for just one more. So we've got a question from Farhan Longat, who asks, do the carbon emissions consider the outputs produced from chemistry labs? And did the extract systems have scrubbers?
So in terms of carbon emissions from chemistry labs, yes, in terms of power consumption, but not in terms of embodied carbon of whatever chemicals and things they might use. So basically, we've only considered the carbon emissions associated with the usage that we can meter. So not with the stuff, any stuff that has to be brought in a sack truck through the door or what have you. That's not included in the carbon model. It's only the stuff that we can meter. So the power coming in and out of the site, and the biofuel and things like that, and the water. That's the only things that we've actually included in the carbon model. So what's the other half of the question again?
So did the extract systems have scrubbers?
So the extract systems don't have scrubbers. It's relatively uncommon to put scrubbers in fume extract systems. You generally rely on dispersal, that whatever chemicals they're using, they get so dispersed into the atmosphere that there's not enough to have an impact on anybody. And actually, a lot of the time, these nasty chemicals are actually things that are in the environment. They're just at a very low level, and you wouldn't expect to come across them. But we did have, we had to make sure our dispersion was very good on this, because downwind of the building is the Nottingham hospital. And one of the chemicals they use in this laboratory is very pungent. So we had to be absolutely scrupulous that enough of this very pungent chemical that you only did a very tiny amount to smell didn't end up in the intakes of the hospital, because that would cause a big problem. Just in terms of that, we did design the flues to be taller than normal to get a better dispersion, and also so we needed less energy getting the fume away.
Amazing. Very thoughtful. Must have taken, yeah. So many meetings, so many emails.
Yes, so many meetings, so many emails. I think one of the things that I find interesting, I think it's pretty much the same with anything. In a way, there's nothing new in the building. It's pulling together of a whole load of ideas and a whole load of things we've done before, if that makes sense. But it's pulling them together all in one building and making sure you do everything. And I think it's true of most engineering. There's very new that's actually completely new. Very little that's actually completely new. You're always pulling together ideas from other places and pulling different bits and components together. It's very little that's actually a complete clean sheet, never been done before. It's always an evolution of what's happened before.
Amazing, awesome. Okay, well, thank you very much, Matthew. It's been really brilliant to have you. And thank you for Michael and everyone who's attended. So that's been really good. Great to see you all. Join us again soon in the continuation of the Engineering Career Series. There will be more. But for now, thank you and have a wonderful evening.
Thank you.